Okay. At this function, we're finding gradient, everybody pretty good on that one. And then graph g of x equals 36, and g of x equals 36. This is pretty clearly left-hand side of the equation of an ellipse. And this is constant, which it is, okay? If this wasn't constant, we wouldn't have an ellipse. So people, kind of do solve for y, and y is plus and minus, whatever. And you ought to be able to do that, but need to recognize conic sections. Okay. Okay, so what's the gradient of g then? It's 6, 0. And people pretty much get that. A couple of mistakes with partial derivatives, but the gradient of g we'll write it like this. And then the partial of this with respect to x is 2x. And the partial with respect to y is 8y. There's your gradient. Okay. And the gradient of x the gradient of g 6 is 0. I'm reading my own 6 is 0 now. We got me started with that. Okay. Gradient of g is then right now the whole calculation is very obvious, comes up 12i. Then we graph this thing. Well, the graph has fits inside of twelve by 6 rectangle with vertices at 6, 0, negative 6, 0, 0, negative 3, and 0, 3. And of course, 6, 0 is a point on this graph. Now, gradient of g is 12i. Gradient b at 6, 0 is 12i. Now, what would be the gradient of g at 0, 3? Well, very clearly, how you put 0 in for x, 3 for y, and you get 24. Check. Okay. The gradient of g here is 24j. At 0, 12, 12, 0. Okay. Well, it turns out that the gradient is perpendicular to this curve at every point. Because this is a level curve of the function u of x equals x squared plus 4y squared. Okay. seeing that in some of your homework. If you draw all the level curves, the eye ellipses, geometrically similar. And the direction of increasing C, and this Q of X equals C. So we have Q of X equals C for various C values, topographical map. Q of X can be sketched in 3 dimensions. It's a very simple quadratic surface. Okay. This is elliptical paraboloid. What's the direction of maximum increase? Well, can't read that word. That says increasing C. The C increases go out, because the bigger this number is here, the bigger your ellipse number. That should be straightforward. Okay. Well, increasing C can go this way, increasing C can go in this direction, go in this direction, can go in this direction. Or it can, you know. Okay. As you move out along arrows perpendicular to the curve, you have the direction of maximum increase. Okay, if you're at this point, I didn't draw perpendicular very well. That is like this. I'm at this point. My direction of maximum increase is the direction that goes most directly to the next curve. So right there's my gradient. And so the gradient is always perpendicular to the curve. And we're going to come back to that when we talk about Lagrange multipliers, but I wanted to establish that right at the beginning. To at least more or less convince you that it's true. Okay. Now these vectors are shorter than those, but I'm just kind of indicating the direction of the gradient. And the problem we're going to have is, let's say we've got a temperature function here. Now you can actually, you know, if you're physically think of an electric field of a point charge here, with the gravitational field of the Earth, which is pointing toward the Earth, right? So you got a planet here, and just look at, you know, and represent the planet as a point at its center. Okay. Some gravitational mass, and the vector field represents gravitational attraction is always radial toward the planet. Okay. At what point or points on this curve would the gravitational field be strongest? If you're traveling along the curve, then gravitational field is strongest when you're closest to the planet. Weakest when you're furthest away. So here you have the weakest field. Now it's increasing, increasing, increasing until you get here. Okay. Then it's decreasing, decreasing, decreasing. Then it starts increasing again. Maximizes here, decreases from there. I'll take this one step further. If I've got a gravitational field, And the direction of gravitational field is always along one of these radial lines. It's directed inwards, so we could have gravitational field here, gravitational field here, a gravitational field here, here, here. And of course, it's getting bigger as we get closer to the wider stuff. Okay. What I want you to look at is where is it that the gravitational field is parallel to the gradient? Okay, so I don't remember if I drew these radial lines while the camera was on or off. But these radial lines would indicate the direction of a gravitational field of a mass at the center. And the vectors, then at every point of the curve, the vector that indicates the gravitational field that represents gravitation would be toward the center. My question is, where's this gravitational field parallel to the gradient on the curve? Well, here, here. There's the gradient, there's gravitation. They're equal, they're in opposite directions, but they're parallel. And here. Okay. Now, where do you have the extreme values of gravitational field? Well, at the point where you're closest to the planet, where the match, and at the point where you're furthest. Okay. So you find your extreme values of the gravitational field on this curve by determining where the gravitational field is parallel to the gradient, where this is a level curve. The gradient of the function of which this is a level curve. Okay? So that's pretty much the Brown multiplier, but we'll come back to that. I want to give you that image. Then think about what happens 3, 4, 5, 6. Well, it's easy to do it in 3, 4, 5, 6 dimensions. It's not hard to visualize in 3 dimensions. Okay, you can say you plan it. Okay, and out here's some ellipsoid, right? Well, where the ellipsoid is closest to the planet is a point where the ellipsoid is closest to the planet. Two things happen. That ellipsoid is a level curve of some function. Okay, I mean the ellipsoid could be 4x squared plus 16y squared plus 81z squared equals some number. Gradient is going to be just analogous to this. You'll have a z coordinate. Okay. So you just set that equal to whatever number, and you have a level curve of the function 4x squared plus 16y squared plus 81z squared. And it can be, rigorously proven that intuitively see that the level curves expand out over similar ellipsoids, and the direction of maximum increase is going to be perpendicular at every point to the level curve. Like, wave my hands about there. Okay. So, and if you go into higher dimensions, whatever this function is, its gradient has to be parallel to the vector field that you're trying to maximize. Okay. Or to the quantity that you're trying to maximize. In this case, we weren't really worried about the vector field, but we'll talk about that. Okay. Okay. The function f of x That has a relative with it. F of X has a relative maximum at a critical point. Why? Because a critical point is a point where F prime of X equals 0, which means that the slope of the function is 0. So if you got a function, it's only going to have a maximum or a minimum, relative maximum or minimum. If it's level at that point, meaning its derivative is 0. So, 0. Okay. So that's just from what you already know. So if F double prime is greater than 0, that means the function is concave up. If it's at a critical point, that means that's going to be a minimum. If it's concave down, it's going to be a maximum. If you have a function of two variables, if that next one has a relative maximum minimum, it's at a critical point. That's where Fx and Fy are both 0. Now, Fx and Fy can both be 0, but you don't have a maximum. Okay. For example, if you have a saddle point goes like this in one direction and like this in another direction. So you're sitting in a saddle, legs go over this way, and this curvature keeps you from sliding forward and back. Okay. So at a saddle point, concave up in one direction, concave down in the other direction. There's no maximum, but there certainly is a point right there in the middle of the saddle where everything's level. Okay. Makes sense? Saddle points show you that just having Fx and Fy both 0 doesn't guarantee a maximum minimum. It does more or less under most circumstances tell you probably either have a maximum or a saddle point. Because there's 3 possibilities. And there's a rule for that. Very simple rule. Here's your test. It's a second derivative test. If this says your second x derivative times, sorry, your second y derivative, it's not close. Okay, first place, you expect if your second x derivative and second y derivative are both positive, well then, you got a saddle point. Well, let's look at the second. If you've got a saddle point, your fxx is positive, your fyy is negative. Well, that means fxx times fyy is going to be negative. It ain't going to be zero no matter what fxy is, because subtracting the square of fxy, right? Okay. So why do you subtract the square of fxy to get this criteria? Because you think, okay, if fxs, if fxx is positive and fyy is positive, then you sure enough expect that you got like the point of a parabola with minimum or maximum point. Well, got a minimum point, okay? That doesn't take account of the fact that you can just have a saddle point, turn around, and it goes down at the 45-degree angle. So it's up here in the x direction, it's up here in the y direction, but you go in the direction of 45 degrees, it's down again. So if you turn a saddle 45 degrees, both fxx and fyy could have the same sign. Okay. But you still have the fxy, which tells you what's happening away from the coordinate axis. Okay, I'm being vague about it right now, just trying to be intuitive, but it comes down to this rule. Okay. Now, of course, if fxx and fyy are both negative, well, that would imply a maximum. Unless somewhere in between the x and the y axis, you have a follow up because fxx and fyy don't measure that. fxy does. And we want to talk about why that is intuitively. And prepare you to understand the homework. But that's the rule. So if these equal zero with their and fxx fyy minus fxy squared is positive, then you have a maximum. Relative maximum or relative minimum. This thing is less than zero, then it's a saddle point. And if it's equal to zero, then this test doesn't tell you whether you have a maximum or saddle point. And then you got to go to some other test. Okay. So very handy test except when it fails. Then you got to think of limits along different curves that approach your critical point. and see what happens. Um, but let's suppose four minus 9, we're going to test for maximum, minimum, or saddle point. Five tests, see what it tells. Okay, well, hopefully everybody has their critical points now. Okay. fx equals fy equals 0. Okay. The only way those are both 0 is if x and y are both 0. So there's a point, there's only one, it's at the origin. No, what's the test tell you? Well, it tells you that. X is 8, FYY is 18, FXY is 0. Now we actually call this a discriminant. We use, I think, capital D, I think that's what text use, that's what most text use. Okay, capital D equals you don't have to multiply that out. All you gotta do is say, okay, so less than 0. Positive times the negative numbers less than 0. Then we got a saddle point. Now for this particular function, it's just its graph is over the blocking surface. Look at it right as z equals 4 minus 9y squared. Okay, that's a problem. Vertex would be plus or minus. Or the 0 to 0. And this is going to equal some positive number. If X is 0, there's no Y that will make this positive. If Y is 0, yeah, we have an X that makes it positive. You just solve 4x squared equals Z. Get X squared equals Z over 4. X squared is Z over 2. And that doesn't really matter. This point then is for different values of Z. Here's your X and here's your Y. You've got graph and you can think through it. Gonna have. Okay, this is for smaller value of Z, this is for bigger value of Z, this is for bigger value of Z. Gonna have I for one. For each of these. Okay. It's starting to look, it's gonna be a little scary. This is a space-time diagram to the approach to the event horizon of a black hole. Okay. And I've been looking at a lot of these diagrams. Trying to really understand it. Yeah, but somebody really. And how you got this. So what's it look like? The Z's increasing, so Z's coming out of the. Board at you. And have this shape, right? Of course, you can do the intersection with the XY plane. The XZ plane, you get Z equals 4x squared. Just right. And actually, wait a minute. Well, that disturbs me. I'm not gonna worry about it. Okay, there you have it. Now, if Z is less than 0. I should have used vertices there, but I'm talking about more than once. Vertices would be 0 plus or minus square root of Z over 3, because this will be equal to a negative number. But then we just, write it as 9y squared minus 4x squared equals negative of Z, right? And it actually ought to be square root of negative Z. 3. Because Z is negative, so that's going to be positive, which means I can kind of superimpose it here. More fast and come now. Yellow right there, boy. There. All right. A good little basket. But now you have a bunch of hyperbolas going like this. So that, now you got a bunch of yellow hyperbolas below. These are all below the x-axis, so you got kind of this. And it's shifted 90 degrees. Okay. In the XY plane, you have only the origin. So it's like you have this first set of hyperbolas coming out of the board like this. Getting smaller and smaller as you approach smaller and smaller values of Z. Until when Z equals 0, you just have the origin. You got these things that shrink down to the origin, to that point, and then you have a bunch of them that are oriented at 90 degrees. Think about that, it's going to give you sound in this direction. Okay. So try to reconcile your visualization of that. Might be convincing. Okay. Well, there's your technique. Now, there's a little more to it. We're going to kind of let you figure out because we need to talk about those Brown's multipliers. Okay. That's the thing where you have level curves and all that. Okay. So oh, here it is. Okay. Well, go back to this picture. Let's stick with this G of X function. We're going to kind of see how this test works out. Okay, now this is what we've already determined. If G of X is this, then the gradient of G is this. Simple enough. Find the gradient of F. Should be able to write that down pretty quickly. Okay. Well, the derivative, well, the gradient, okay. This is the gradient of F. Use the chain rule. And I'll scratch it down here just real quick. But if you need to review, take your derivatives, then please allow me to review it. You've got to take some big derivatives, of course. Okay. First of all, derivative with respect to x of 1 over. Better get the square root of that square plus 9 to demonstrate this. Okay. Derivative of the negative 1/2 power is negative 3/2 power. Okay. This is f prime g of x. This is your g prime of x. You see this as a function of a function, composite function of the reciprocal square root of the negative 1/2 power with the x squared plus 9 function. And you do the derivative of the negative 1/2 power, which is going to be negative 3/2 power, and I can screw that up because I should have had a negative 1/2. Okay. So there's derivative of your negative 1/2 power of your f function is a negative 1/2 power. So there it is. I don't want to write it out in gory detail. I want to remind you and then tell you, you really have to know the chain and how to do it. And you're going to have to do intervals too. So you might want to review that in the past. So anyhow, your g prime of x then, well, there's your g of x. But you got to make sure you understand composites, how to deconstruct composites, but you did it in calculus. So very important. Okay, well, you apply that to this. And you find that your partial with respect to x is going to be going to have a 2x, right? They got a 3/2 power here. It's just huge. Maybe I need to review. Okay, well, it's a -1 power of this, right? Derivative of -1 power is a negative. The -2 power. And then the inner function has derivative 2x, 2y, or 2z. So I don't know why, I wrote the 3/2 down. That's what I'm thinking. Or we've done a square root of this, and that would give you the negative 3/2 power. So I had that kind of swimming around in my head. So I really can't do it. Okay, anyhow, there it is. And I'm writing it this way. Okay, for example. It's this. The negative to the negative 1 power. Okay. So here it again is your f prime of g of x. And here's your g prime of x. Change. There's the gradient. Now, the question, the thing we have to really deal with here is, where is the gradient of F parallel to the gradient of G? I can remember in terms of this example, we're trying to find the maximum of G of the level, the maximum value of F on this level curve. Okay, so that's written in opposite. It could be written either way, but I think convention has the lambda in front of the delta G for the delta G. So can you write out this condition? Or this function, and you know what? I'm thinking 3 dimensions because that's where we're headed. But this is just a function of 2 variables, and we're doing this in 2 dimensions. So you can leave off all your z's, including the zk. So then this equation just becomes this. So find me a value of lambda that makes that true. There are 2 such values. What I just said before you get into this, I said find me a value of lambda that makes this true. Find the value of lambda that makes this true for some point. Okay, because clearly, if it's true for this, then x has to equal lambda times 2x. So lambda would have to be 1/2, right? But if lambda is 1/2, y is not equal to 8 lambda y, right? 8 times 1/2 y. Okay, so these can't simultaneously be equal. If you write this equation out, separate your I and your j. Then you should be able to find a lambda. Okay, well, what we get is, this equation is true, then the I component has to equal the I component, and the j component has to equal the j component. Now, as you're going to see, we're still going to end up with only 2 equations and 3 variables. So we're going to tweak u of x to make it work, okay? So 2 equations, we're going to have I'd normally write lambda x, lambda y, because it replaces goes in front of it. English letter. We have three things that we don't know. We don't know x, we don't know y, and we don't know lambda. Okay. So we need a third equation. Well, the third equation I'm going to get by just tweaking my g of x function. If I want to find the maximum on this specific curve, I got to get specific about g of x. So what I'm going to do is I'm going to make g of x equal to this minus 36. Then this curve becomes curve g of x equals 0. Okay. So my curve the problem is this. So now I can say it's g of x y. So I'm just going to say x squared plus 4y squared minus 36 equals 0. I could as well have said x squared plus 4y squared equals 36, which is identical. But the way the theorem is usually phrased, to accommodate every possibility, you just say g of x equals 0 and put your constant over this side. Okay, just put everything over on one side, whatever your curve is. Okay. Now this can be solved. It's kind of a mess to solve, so we're not actually going to solve it. But that's the process. And most of the correct equations you have will be nice and linear. And if they're linear, it's not technical. And if they're not linear, it's going to be still linear. It's not difficult, but I can tell you that these equations are solid if x equals 6, y equals 0. Now, if x is 6 and y is 0, we can figure out lambda. Okay. So lambda is going to equal 1 over x squared plus y squared squared. X is 6, y is 0. That was going to be 1 over 1296. If let's say y, lambda is 1 over 1296. And if x is 6 and y is 0, this one's automatically solved. You get 0 equals 0. Okay, so there's a solution. Okay. times 1/1296. Same is true if x is -6. So if we say x would be plus or minus 6, lambda is 1/1296. And the value of lambda doesn't really matter. What this tells us is you have an extremum at 60 and another one at -60, which is exactly what has to happen for a function like this. Why? Because this function has a gradient which is just a multiple of xi plus yj. Xi plus yj is just the radial direction from the origin. So everything comes around here. Okay, and then here, x would be 0, y would be plus or minus 3. Because if x is 0, then this one's satisfied. So whatever satisfies this. And you got to get lambda equals -1/4. And this should have been -1/1296. In careless. So you're going to get lambda equals -1/4 of this, which is going to be 5200 minus 12, 14, 51, 88. What's her name if that's wrong? I kind of think it's right. No. 4, 80. Okay. I think that's probably right. There it is. Okay. Now where do I get x equals plus or minus 6 and y was plus or minus 3? What is this equation? I can eliminate variables one at a time. I solve this for y. Plug that in for every y. And then I have just equations of x and y. And x is lambda, eliminated y. Okay. Then I can solve this one for lambda and plug it in here. It's a mess. So I didn't want to go into it. But the process is very straightforward. I don't know if it's still over more. I'm way off. Everything I did except write out these solutions, which you can verify. Works. So the ultimate result is I just evaluate this at x equals plus or minus 6. Evaluate what this. And I find the maximum value or the minimum value in this case. And it's going to be 1/36. Okay. And then plug in y plus or minus 3, which squaring it, so it doesn't matter, it's going to be 1/9. So this function will have its minimum value of 1/36 here, maximum value of 1/9 here. As we go around. Okay. And you want to keep that image in mind. Now, if you go to 3 dimensions, you have another variable. You're going to need another constant. Okay. And you can see how that goes. People usually don't have any trouble with that once they see that. Okay. Well, that's good timing.